In this video, I'd like to talk about dimension reduction, and specifically principal components analysis and factor analysis. Principal component analysis is a mathematical way of reducing the dimensionality of a group of variables. Let's say we're going to do the BIVS survey. And it has 28 questions, and we want to reduce that. Well, we can just do a simple mathematical reduction of the dimensions. But that doesn't allow us any interpretation of factors. In other words, the items are grouped together because that's the least random. Factor analysis, on the other hand, and I might add this is exploratory factor analysis, is similar reduction of dimensions, but you can name these, and the reason you can is because there are correlations with underlying factors, sometimes called latent variables, and then there is unique variance for each question that's not really part of the factor. So the factors are pure, and it makes some sense to be able to label them. Now, to do this, we're going to go through a series of steps. We're going to test overall for scale normality. We're going to eliminate the missing data. We're going to select a training data set. In this, for example, in the BIVS study, we use first-year optometry students. We're going to standardize all questions with z-scores in the training data set. We're going to run a principal components analysis in order to determine the number of factors that are most likely to be used. And then we're going to do a factor analysis on the training data. Then we're going to get some factor scores from this, and we're going to apply those factors to the complete data set. And then finally, we can test the groups and see if they differ. So here's our data set. We have ID, the group. We either have TBI patients, third years, first years. And we have the age group, and then 28 questions. We happen to also give the total score, but we're not really going to use that. Okay, so the first thing we need to do is we're going to define our data training set, and we're going to include those people who are our first-year optometry students, and that happens to be the group that's numbered 5. And so that eliminates everybody but those at the bottom of the list. All right, now we want to check on our QQ plots. We want to know if our data is normal. So the way we do that, descriptive, QQ plots, and we come down here. We're looking for the normal distribution, and we're going to say OK. And it's thinking about it. And here we go. Now remember, in order for this to be considered normal data, and remember the reason we want to have normal data, a QQ plot takes the quantiles of various quantiles of our observed data, which is our Likert scale that goes from 1 to 5, and our quantiles, matching quantiles from the expected normal, standard normal deviation. And if this relationship is linear, then a 1 unit shift down here will be equal to a 1 unit shift here, and that's anywhere along the line. And so we can say that our data is approximately interval. Now, to the extent that these little dots don't fall on this line, we are deviating from normal. And actually, this has some issues with it. These aren't terrible, but they're not great either. This is pretty good. Unfortunately, we only have 5 points on our scale, so it doesn't give us a lot of wiggle room. You're okay. Okay. Not too bad, not too bad, not too bad. Just go down through. Now that one's not so hot. That's question 9. So we need to be a little bit concerned that question number 9 is not linearly related to the to a normal distribution. So that's an issue. And in fact, I think we're going to find that the next few are not too good. That's question 10. And then we have, 11, not the best. 12 is not too good. We're going to basically, oh, that's pretty good. We're going to basically not worry about this too much, but we're going to note the ones that were off. What was this one? 14. And then see if those happen to be ones that don't fit our analysis very well. That's 19. Not too good. Oh, 20. 21. 22. This is why we do a Roche analysis when these are bad, but sometimes the Roche analysis is not necessarily appropriate. 23, 24 is okay. It's a little off. 26, 27, 28. Okay, so we have some questions there that don't really fit the normal distribution, and it's somewhat questionable as to whether proceeding with a statistical method that assumes linear or assumes normal distributions is somewhat questionable. Now, if you think about what does our distribution look like, let's do some frequencies. Oh, that looks pretty good. Oh, those are descriptives. Cancel. Descriptive frequencies. Oh, not okay. What do we go down to? 28. See what that looks like. I forgot to. We want to look at the plots, histograms. And look at how skewed these are. Now we're saying that we're talking about comparing to normality. Just as a reminder, if you look at this curve and you think of a normal curve as starting over here and being bell-shaped, these are symptoms. Now that's kind of a high peak. These are maybe a little high in normal. In fact, this was a question 23 was one that didn't fit that normal distribution very well. If we come up here to question 1, that was better. Now you can see how we're looking basically at the right tail of a normal distribution. So this is a symptom where you don't feel well, but there's a whole thing about how good you could feel that's basically chopped off. So it's a cumulative distribution. It's just that most of the observations happen to fall at 0 or better, and then a scale of 1 and so forth. So it's not a scale from 1 to 5, it's a scale from 0 to 4. And you can, and it's a cumulative normal distribution, so you might start around 50% and then trail off. So this is perfectly fine to call this a normal distribution if it falls out to be straight on the other end. So that's checking for normality. Now another thing, the next thing that we do, that's pretty common or often recommended in principle and in factor analysis, and that is to standardize the scores. The way we do that, again, we're just working with the first years and their scores. They took the test right after they started optometry school. They're pretty fresh. Their eyes haven't been beat to death yet. And so we go 1 to 28, and we're going to click on this Save Standardized Values as Variables. So what that's going to do is it's going to go through and it's going to give us some new variable names, and they're all z-scores. So they're z-scores that correspond to each variable. The other thing this does, it's going to give us for each question for the first years the descriptive statistics. So let's save these, and we have them ordered. Here are the questions. We're going to put them right here because we're going to need these means and standard deviations later. We have only done the standardized scores on the first year optometry students. We're going to need standardized scores for all the cases. And so in order to get that, we're going to need the mean and standard deviation. So let's go back to our SPSS and let's start looking at our dimension reduction factor. Let's go to our principal components. We're going to just do this quickly to see which variables or how many factors we want to consider. Let's get rid of all this junk. Oh, I can't do it that way. All right. So let's just say OK. Now, on this analysis, we get, well, let's see. Communalities aren't going to make too much sense on this one. We have 9 factors. 9 factors. And because it has stopped, if we go over here, we can see that it stopped listing them over here when this number 9 and number 10 falls below 1. Now, why is that? So these are called eigenvalues, and eigenvalues represent the amount of variance accounted for within a particular factor. So the first factor has 5 units of variance. So there's 28 questions, all with a mean of 0 and a standard deviation of 1. And so if we summed it all up, summed all these numbers up, we would get 28, and that's 100% of the variance. Well, a factor that accounts for equivalent to 5 questions is pretty good. That's 3, 2, and so forth. Now, when we get down to the 9th question, there's a whole factor that's really only accounting for basically 1 question. And that doesn't seem very useful. So we're going to actually, even though it says 9, it gave us 9, we're going to tell the system to run again, but only look at 8. So let's take a look at our dimension reduction. We're going to extract a number of 8. Rather than based on eigenvalues greater than 1, we're going to tell it we want 8 factors. And we're also going to tell it we want to do a principal axis factoring. So we want to do factor analysis. Now, we want to consider that unique variance so we can kind of interpret the questions. And we're going to choose equal max Equal max rotation. If we hit F1, I think we'll get some help. Maybe not. That's too bad. Oh, there it is. So, come on, baby. Time's burning. Okay. Varimax rotation. This is a little help screen that lets you know what kind of rotations there are. These are all the choices. It's sort of like the choices of covariance matrices. Oh, geez. And we're going to pick the equal max, a rotation method that is a combination of Varimax, which simplifies the factors, and Quartimax, which simplifies the variables. The number of variables that load highly on a factor and the number of factors needed to explain a variable are minimized. So that's what we're going to do. So let's see. Continue. And we're not going to write our scores just yet. We're going to save them as variables, but we're going to do our analysis first, and then we'll run it one more time and save our variables. Under Options, we're going to sort by size, and we want to suppress values less than 0.4. Now, I'm only doing this because it's easier to see the output. But what that is our correlation with our factor has to be at least 0.4. And we'll see what that means in a second here. Okay, now when we go and do the factor analysis, we now have this unique variance that is variance where the question is not related to any of the factors. But if we were to do a multiple regression with Q2 through Q28 being the independent variables, and Q1 is the y, so y equals Q2 through Q28, our r squared in this multiple regression kind of thing would be 0.606. Then if we looked at question number 2 as a regression with 1, 3 through 28, the r squared would be 0.448. So communalities are the correlation between the variables and all the other variables in themselves. So extraction, we didn't use all the factors that we could have, and so we reduced it a little bit. And so that's when we only use the factors to correlate question 1, we can only account for 53.53% of the, or 53% of the variance. So here we have total variance explained. Same thing. Notice the chart is just like the other one. We have our extraction over here, and then our rotation. Notice that it robs from Peter to pay Paul. So we reduce this first factor a little bit, but we increase the other ones a little bit. So it balances out the factors. Rotation balances out the factors, and this is again, it's a mathematical thing. We're not doing anything by hand, but it just clusters the questions together a little bit better. And here's our rotated factor matrix. Now let's look at these. So we've used the z-scores. We've got question 24, 25, 26, 27, 28 all clustered together. And these are called factor loadings. And so this is factor 1, and these are the loadings. Well, what's a loading? A loading is the correlation between question 25 and its factor is 0.89. The correlation 24 is 0.807. So you can see these are all pretty highly correlated. Question 28's, not as good, but it's, it's in the neighborhood. So we see that all the way through. If we come back up here for a second, total variance explained, our model is only accounting for 53% of the variance. So that's actually not that super. So it is not unsurprising to see that some of our correlations with the factors are not too great. Now, one of the things that we have here is that we have one variable, question 22, is correlated heavily on two factors. It's confused. So one of the things we might do is drop 22. But before we drop 22, if we come down here, we can see that some questions just weren't correlated with anything. Now, unfortunately, because everything's correlated from everybody else, we can drop question 13, but we don't want to drop all the questions at once. So right now we have 1, 2, 3, 4, 5 questions that it looks like we want to get rid of. But let's look at question 14 first and get rid of that, run it again. Look at our factor matrix. And now we have some more correlations. That kind of muddied the water a little bit, actually. We have one more down here, Q11. Why do we start from the bottom and work our way up? Because the factors tend to be weighted from the top down. You can also look at our unrotated factor matrix and see that numbers tend to be, well, if we had left in, not filtered out, these are blank because we got rid of all values less than 0.4. If we hadn't done that, we could have seen some things. So how is our, and notice here when we got rid of that last one, we actually fell below 1 there. So we should probably run this again, but only ask for 6 extractions. So let's do that. We're spreading our factor too thin by getting rid of that. So extraction is now 6 instead of 8 because we have 1, 2, 3, 4, 5, 6 that are greater than 1. Although that last one's kind of small, but let's see where that leaves us. Oh, so we lost that guy on that one, so we should have probably gotten rid of him. So let's get rid of that. Let's not extract 6, let's extract 5. That one was right over the edge and it fell off rather than getting stronger. So let's just do 5 factors. All right, how about that? All right, now everybody's over 1 and probably enough that it can survive. Let's look at our rotated factor matrix. And we have a lot of questions that appear to be irrelevant under this reduced factor loading. If you remember from the paper, there were a number of factors that were correlated with each other that dropped out, and hopefully we're getting rid of those here. I don't know, we'll see when we're done. So let's look at this. Let's get rid of question number 2. And how did that affect our total variance? Ooh, we're right on the edge there. Probably may want to reduce it to 4 factors. Let's see what our rotated is. Let's get rid of question 11. And that might have taken us over the edge on our variance. Yep. So we want to go down to 4 factors. There's a little bit of an iterative process. Extraction, we want 4. So first you want to see everybody's above 1, and then you want to see who is not in the model. Because when they're not loaded on a factor, they're kind of getting in the way. So everybody's well above 1. But we have question 23 that looks like it could use some help there. Dimension reduction. Question 23 we're going to get rid of. And how did we do on our total variance? We're still above there, okay. And what did that do for us? 128, we went down. Notice we're now down to 41% of the variance accounted for. So we're cleaning up our model and getting better factors, but we're losing accountability of our variance on the way. It doesn't really change the percent variance. As you get down, you just, it's tightening up. All right, let's look at our rotated factor matrix. All right, we're down okay there. We have these 3 guys, so let's get rid of question number 9. And how are we here? 1.2. We're still good, but well, let's get rid of question number 4. Now, one of the things we'll want to do when we analyze it is determine if we have more information that is important. So this isn't changing. So those 3 questions, we've been getting rid of each one of them, and it hasn't filled in the others. So those were probably, they could have been related with each other as to form another factor, but question number 13. All right, so hopefully this will do it for us. We're still over 1. Good sign. And our balance is, it's still a little off on there, but it's okay. We're only accounting for 8%. So these factors are there's a lot. What this says is there's a lot more information out there that that this test is probably not covering. So, but another thing is we're just doing first years. And when we just do first years, we're truncating our range of possibilities. So we could be going through this whole exercise just because we've penalized ourselves too strictly with range restriction. All right, here we go. 4 factors. Interesting. Okay, so let's score them now. We're going to just have these 4 factors. We're going to look and see what they are in a minute. And this is reduction, factor, scores, save as variables. We want the Anderson-Rubin. It has a mean of 0 and a standard deviation of 1. It's pretty handy. And if we look, we can now see on our see on, where's our output? Our file. Here we go. Variable view. We're going to get rid of these factors because they were left over from before. We have 4 factors. All right. And so when we look at these, come down to our first years. This is everybody's score. Now, remember, it has a mean of 0 and a standard deviation of 1. So we could convert this to scores on a scale from 0 to 4, maybe to make a little bit more sense on various things. But we don't have anybody up here. So the next thing we have to do is score. And I think I'm going to break this video at this point. And we'll do scoring on the next video.